Okay, so once again, it's week 5 Thursday, which in a normal quarter would be like your halfway point, but in summer quarter it's like the week before finals. So it's a little crazy. I hope you've kind of enjoyed the class at least. Okay. There are student evaluations right now, I think, and I think that's due on Tuesday, right? So if I may ask you the favor of filling out your student evaluation, I hope you liked it. I hope, or at least you found it interesting. I don't know. It's hard. And then, and if you really like the course, please, please consider writing a review on like Brew and Walk or Rate My Professors or something like that. I would also greatly appreciate that as well. So yeah, next Thursday will be the final. I'll try to avoid. So on Tuesday, I don't want to cover like too much new stuff. We can spend some time doing review. Maybe I can do like a neat example of some of the stuff we learned today, and then and we'll go from there. So I guess everything I cover in today's lecture will be fair game. Everything that's covered in your currently assigned homework will be fair game. Next week, I might have like a very easy homework assignment or something for you to play around with. I don't know. Did anyone play around with the cipher code and decode the messages? Did that work out? Okay, all right. I got some smiles there. So I don't know. Maybe they're both like quotes from, I don't know, stuff that I've enjoyed. So all right. Anyway, questions before I get started today? Okay. All right, then we'll go in. I'm gonna try using OneNote again. It seemed I got Sketchbook working again, but we'll try this OneNote stuff, and maybe. Well, I don't know. Do you guys have a preference? OneNote kind of prints it out onto like regular size things rather than. No preference. Either way. Okay. Well, we'll see. All right. So every now and then I do like to throw in kind of our. Well, I don't know. Okay. So far, what we've covered is the Metropolis algorithm, and the Metropolis algorithm, or Metropolis Hastings algorithm, which is its generalization, allows us to get a representative sample from a target distribution, even if we can't sample from the target distribution directly, right? And it also allows us to avoid finding the normalizing constant. Okay, so we have Metropolis Hastings algorithm. Okay, and this allows us to draw a representative sample from a target distribution. And the whole reason why we want to draw a representative sample from the target distribution, why is that in the first place? Because that's what we do in Monte Carlo methods, right? Is that we're avoiding the math, and we're gonna just take the representative sample and take the mean of that, or apply the function and take the mean of that, and stuff like that, right? So it allows us to draw a representative sample from a target distribution, and We draw samples in Monte Carlo methods. To avoid math, right? Okay, and the strength or the advantages of Metropolis and Metropolis Hastings is that, or the advantages of Metropolis and Metropolis Hastings are that, you know, we do not need to draw independent samples. Okay, just set up a Markov chain. Okay, and we also only, we do not need to calculate a normalizing constant. We do not need to find normalizing constant of a PDF, okay? So we don't need to find the normalizing constant there. Okay. And so far all of our examples have been unidimensional. And it can be extended to a multivariate context, okay? So Metropolis and Metropolis Hastings to a multivariate context. And it's very sorry, I'm trying to oh dear. All right, so we can extend Metropolis and Metropolis Hastings to a multivariate context. All right, and so the way it works is pretty much exactly the same. Okay, all right. So the way it works is pretty much the same. All right. All right, so let's say we have a two-dimensional probability distribution. Okay, I don't know, maybe, you know, for example, multivariate normal. Okay. All right, and so the multivariate normal, I don't know, it looks like this, right? I don't know how to draw this thing. It's something like that, right? Okay, right, and then so if you plotted this on a contour Or maybe if you just drew samples from it, it may look something like this. Right. So let me go and just find something real quick. We'll go to multivariate normal distribution. All right, we'll go to the Wikipedia page. So there's your multivariate normal distribution. We say it has this notation and this PDF. What's going on here? Why am I having such trouble? Okay, so we'll say, yeah, we have okay, we've got this, and the PDF is the determinant of 2 pi sigma times to the negative 1/2. So it's like 1 over the square root of this, right? And e to the negative 1/2 x minus mu transpose sigma inverse x minus mu. Okay, so that's what we have. And okay, so this is our PDF here. And anyway, that's that. And so let's say so the way the multivariate Metropolis algorithm Metropolis Hastings algorithm would work like this, right? So you start at some arbitrary location. Maybe we'll just call this theta 1 and theta 2. So you start at some arbitrary location, and what we will do is we propose a new location, okay? Which we'll call theta 1 prime and theta 2 prime. Okay. And we to propose a new location, we draw a sample. We draw a single coordinate from a proposal distribution. Okay, and if it's Metropolis, the proposal distribution needs to be symmetric. Okay. All right, and so, you know, maybe, you know, some example proposal distributions. You know, you could have maybe a multivariate independent normal distribution centered at your current location. So it could be, you know, something like theta 1 prime and theta 2 prime are drawn from, you know, the two-dimensional normal, where your mu vector is your current locations, theta 1 and theta 2, and then maybe your sigma is going to be the identity matrix. Okay. And so this would be like, if this is your location here, theta 1 comma theta 2, then you would be drawing just something centered right there, right? Depending on where your theta 1 and theta 2 are, you can draw values centered there, right? So that would be could be a proposal distribution. What else can you think of for a multivariate proposal distribution? What would a uniform proposal look like? It would be a constant, and you would need to have kind of like a plus or minus something, right? So another possibility, these are just examples, could be kind of a multivariate uniform. Proposal. Okay, and again, it could be theta 1 prime and theta 2 prime are going to be drawn from basically uniform, where we have theta 1 minus some factor, I'll just do 1, theta 1 minus 1 to theta 1 plus 1, and uniform theta 2 minus 1 to theta 2 plus 1, right? And so if this is our location, theta 1 comma theta 2, then we would draw from a square centered right here, right? This is a 2 by 2 square. Centered at theta 1, theta 2. So those are symmetric proposals, and okay. And then, so anyway, so I don't know why I'm writing a 2 here. So once you have proposed a new coordinate, then you calculate the acceptance ratio. which will be equal to the minimum between 1 and probability of theta 1 prime, theta 2 prime, the probability of the proposed divided by the probability of the current. Okay, this is for Metropolis. Minimum of theta or Metropolis Hastings. Okay, and then and then you draw U. Zero one to decide whether or not to accept the proposed theta 1 prime, theta 2 prime. Okay, and then if you accept, then you move, and if you reject, then you reuse. The proposed value becomes part of your sample. And if you reject, the current value gets used again in the sample. All right, is that okay? So that would be kind of your multivariate version of the Metropolis algorithm, and basically it just requires you to have a multivariate proposal. Okay, and so for a 2D, you can have a two-dimensional multivariate thing, which we can kind of picture as these hills, and for a 3D, then it becomes these, I don't know, spheres, I guess, or something, ellipsoids. Okay. The issue with the multivariate Metropolis or multivariate Metropolis Hastings algorithm is that if your proposal distribution is if there's like significant mismatch between your proposal distribution and the target distribution, then a lot of values will get rejected, okay? And you'll be in a situation where a lot of values will be proposed, and many of them will be rejected. Okay, so between the proposal distribution and target distribution, many values will be rejected. Okay, so it's kind of hard to picture this, but just imagine your 2D target looks like this. Let's just say it's this very thin distribution like this. Okay, so this is your target PDF. So if this is contour plot of your target. Okay, and let's say we are like right here. Okay, so let's say this is our current theta 1, theta 2. Okay, so this is theta 1 axis, and this is your theta 2 axis. Okay. So if let's say we have a uniform proposal. All right, so we'll zoom in. And okay, so this is our theta 1, theta 2, our current value, and the it's hard to draw this, but this is kind of your thing, right? And so if we were to propose values in okay, let's say this is kind of our uniform proposal, right? So we're proposing between, this would be theta 1 minus 1 and theta 2 plus 1, and this corner over here would be theta 1 plus 1 and theta 2 minus 1, or something like that, right? So we're proposing values in this region, okay? Pretty much, not pretty much, but just, you could imagine anything outside of here. So only this region has a higher probability. So this anything in here will be truly accepted, and stuff out here will get is more likely to be I don't know about more likely, but you know, you might propose some bad values here. Okay, and especially if you know, if we exaggerated it, there might only be a thin sliver inside this proposal region that would be accepted, and everything else would get rejected. Okay, and the problem is magnified even more in higher dimensional settings. Okay, so you know, if it's unidimensional, and let's say 10% is good and 90% is bad, you've got a 10% of hitting it, right? But then if you make it two-dimensional and you say 10% is good on the x-axis and 10% is good on the y-axis, then out of the entire thing, only 1% is like a good region, right? And then if you magnify that to 3 dimensions, then it becomes, you know, 0.001. Okay, your proportion that will get accepted. And as we get into higher and higher dimensions, the uniform proposal, or just any proposal that's not really in tune with your target PDF, is going to have a lot of its values rejected, if that makes sense. Okay, so as the number of dimensions grows, more and more values will get rejected if the proposal distribution does not closely match the target distribution. Okay, so one way to deal with this, if you want to draw samples, we still want a Markov chain that will get us values from our target distribution. One method is the Gibbs Sampler. Okay. Solution is the Gibbs Sampler. Okay, so this is basically so the Metropolis algorithm is one method to design a Markov chain that has a stationary distribution equal to the target distribution. This is another method to design a Markov chain whose stationary distribution will be equal to the target distribution. Okay, and so, with this, you run your Markov chain, and in the long run, you'll be getting samples from the target distribution, which is what we want. Okay, same idea with the Metropolis algorithm. You let the Markov chain run. In the long run, you'll get samples from the target distribution. Okay, so we'll say both, the Metropolis algorithm and Gibbs Sampler are ways to create Markov chains that, when run, will produce the desired samples. Okay, so the difference is that the differences. Okay, in the Gibbs Sampler, we propose only one coordinate at a time. Okay, so in the Gibbs Sampler, we propose only one coordinate at a time. right? And then the Gibbs sampler requires us to do some math, okay, to break down the multivariate distribution into a series of univariate conditional distributions, okay? Okay. We have to break down the multivariate distribution. Okay, into I guess we'll just into univariate conditional distributions. Okay. So, do you guys remember coordinate descent from maybe 102A? And in coordinate descent, it was an optimization algorithm to find kind of the minimum or the maximum. And the way it worked is you conditioned on all the variables except one, so that so the multivariate function became a function of one variable, and then you maximized or minimized the function of one variable, and then you changed it. Changed variables, and then you minimized it based on the other variable, and so on and so forth. It's kind of like that here, except instead of minimizing or maximizing on one variable at a time, you're going to draw a random sample one variable at a time. Okay, so the Gibbs sampler, we propose only one coordinate at a time, or actually not propose, we sample. We sample only one coordinate at a time, and then and it requires us to have univariate conditional distributions. Okay. In the Gibbs sampler, there's no accepting or rejecting. You're always going to be accepting. Okay. All right. So. Okay, so let's say we have our target distribution is a bivariate normal distribution, okay? So the Gibbs sampler requires us to do math. We have to break down the multivariate distribution. Here, wait, actually, before I get into that, let me just do this. Okay, so first we'll call this the systematic scan Gibbs sampler. This is kind of just your regular Gibbs sampler. So if somebody talks about the Gibbs sampler, they're probably referring to the systematic scan Gibbs sampler. Okay. And again, so here, our goal is to generate a sequence of x values, multivariate, coming from a target distribution. And so so this is a vector x at time t. This will be kind of the sequence of x at time 1, oh, I'm sorry, not, you gotta undo this. Okay, so I'm sorry, your x vector at time t is defined as x1 at time t, x2 at time t, x3 at time t, all the way up to xd at time t, okay? So this is just a d-dimensional vector x at time t. Okay, and so at time t plus 1, basically for each I from 1 to d, you're going to generate the value x sub I at time t plus 1 based on the conditional distribution of p of x sub I given x1 at time t plus 1 I see. So using basically all of your latest values. Okay. So here's here's an example. Let's say d is equal to 4. Okay, so then your x vector at time t is going to be x1 at time t, x2 at time t, x3 at time t, and x4 at time t. Okay? All right, so let's say we have run, we're on our first iteration. Okay, so we have arbitrary starting point. We have arbitrary starting location, what? x0, which is going to be x1 times 0, x2 at time 0, x3 at time 0, and x4 at time 0. Okay? For the Gibbs sampler to work, we need to have the conditional distribution. Okay? So our first value, which will be x1 at time 1, will be drawn from the univariate conditional distribution of x1 given the other x values. Okay, so we draw x1 at time 1 at random. So we draw at random x1 from the distribution of x1 given that x2 is equal to x2 at time 0, x3 is equal to x3 at time 0, and x4 is equal to x4 at time 0. So we condition the distribution based on the other values of x. Okay, so that gives us a new value for x1. Okay, then the next value, x2 at time 1, is drawn from the conditional distribution of x2 given that x1 is equal to x1 at time 1, because we just drew this value, okay? Use the value you just drew. Use the brand new value you just drew. Okay, and then x3 is equal to x3 at time 0, x4 is equal to x4 at time 0. Okay, so that gives you x2 at time 1. Is this okay? And then you continue, and so you'll get x3 at time 1 coming from the conditional distribution of x3, given that x1 is updated, x2 is updated, and then you use the old x4 value, right? At time 0. And then lastly, you get x4 from this conditional distribution. Okay, and then so now you have the x vector at time 1 equal to x1, x2, x3, all at time 1. Okay, and then and that's one iteration. Okay, and this is one iteration of the Gibbs sampler. Okay, so now that you have this, then you can start at the beginning, all right, and then you'll look up to draw your values for x2. Okay, x2, you start at the first variable, and then you condition it based on all of the other values you have, and then you go through. Okay, so it requires you to have this conditional distribution, the probability of x1 given everything else, the probability of x2 given everything else, the probability of x3 given everything else, and so on and so forth. Okay, so that's the hard part. The hard part of the Gibbs sampler is doing the math to figure out the conditional distributions given everything else. Okay, but then once you have that, then it's quite sequential. Okay, so you're doing just one coordinate at a time, and you sample it based on keeping everything else at a constant. Okay, and then and you do that. Whereas, the multivariate Metropolis or the multivariate Metropolis Hastings, you had a multi-dimensional proposal, and you would just propose a new point from that multivariate thing. So you would propose, all 4 coordinates at the same time. You'd say, okay, we're currently at location x1, x2, x3, x4 at time 0, and I'm going to propose x1, x2, x3, x4 at time 1, okay? And if it's a multivariate proposal, even if everything were independent of each other or something, all four, it could be a situation where the x1, x2, x3 that's proposed are all reasonable and likely, but the x4, because it's randomly drawn, happens to just be a bad coordinate, right? So it's like, okay, pick some random thing, and because x4 is so unusual, that proposal is going to get rejected immediately. Okay, and so the Gibbs sampler can help us through these situations where we have high dimensionality. Okay, so this is one iteration of the Gibbs sampler. Does that kind of make sense? Right. So that's your systematic scan. We also have a random scan Gibbs sampler, and this, I would say, this is less common, but it can be used. Okay. Okay. Random scan Gibbs sampler. Okay. Basically, the idea is the same. As the regular Gibbs sampler. But basically, at the start of each iteration, you shuffle the order in which you will sample parameters. Okay? Okay, so maybe with d equal to 4, you have x at time 0 being x1, 0, x2 at 0, x3 at time 0, and x4 at time 0. Okay, and then for the first iteration, okay, you shuffle, and we'll sample in the order, I don't know, 4, 2, 1, 3, or something like that. Okay, and then so you'll do x4 at time 1 is p of not equal to, is drawn from. And then you'll draw x2 at time 1 given probability of x2 given what? x4 at time 1. Okay, etc., etc., etc. Dot, dot, dot. Okay, and the next iteration, shuffle the order again. Okay, and then maybe sample in the order 1, 3, 4, 2, or something like that. Okay, and that's random scan. So each iteration you're going to do all of the variables, okay, all of the coordinates, but you kind of just mix up the order in which you'll do this. Okay, and sometimes this can help. Okay. All right. Is that okay? So that's random scan Gibbs sampler. So let's do an example. All right, so we'll do Gibbs sampling for a bivariate normal distribution. Okay. So I think we said, so here we will let our mu vector just be 0, 0, and then we will let our sigma matrix be 1 with covariance rho. Okay. All right, and so earlier we looked this up. Multivariate normal PDF is equal to, what is it, the determinant of 2 sigma pi, or 2 pi sigma to the negative 1/2 times e raised to the negative 1/2 x minus mu transpose sigma inverse x minus mu Alright, so we have this. Okay, if we calculate the determinant of this, of sigma, okay, then it's going to be 1 minus rho squared, right? And then we'll raise this to the square root of that, okay? When you the determinant times this, so we get to pull out 2 pi because when everything is multiplied by 2 pi here, it gets squared, right? And then you pull it out in the square root. Okay, so we have that for this part, and then over here, if I do the vector x minus mu transpose, I'll get kind of just this vector x1, x2 times the inverse of this is going to be 1 minus rho squared, kind of the determinant of this. So when you have this kind of symmetric thing, you can set it up this way. 1 over the determinant, and then x minus mu not transpose will be x1, x2. So the x vector minus the vector mu, okay, but not transpose, will be in this form. Okay, and then, all right, and so if I multiply all of this out, I'll get 1 over 2 pi root 1 minus rho squared. This is a constant, e to the negative, and then anyway, I get 1 over 2 times 1 minus rho squared times, I think, x1 squared minus 2 rho x1, x2 plus x2 squared. I think I did this right. These are my notes here. So here is our our PDF for if we are going to have, if it's centered at 0, 0 and has this covariance matrix. Okay. So far, so good? Kind of. Okay, and then so for Gibbs sampling, we need to figure out the conditional distributions given the other distributions, right? Okay. Okay, so we will draw x1 at time t, we'll say at time t plus 1, from the distribution of x1 given that x2 is the value at x2 at time t, and then and x2 at time t plus 1 okay. So, in a systematic thing, right, you draw x1 first and you use your current value of t, and then once you get that new value of x1, then you'll use that to draw your next value of x2. Okay, so basically we need probability of x1 given x2 and probability of x2 given x1. Okay, so basically I'm going to just do one of these, and then I'll say all we have to do is just swap the symbols x1 and x2 and we'll get the other one, because the thing is symmetric, right? But anyway, so probability of x1 given x2 is going to be the probability of x1 and x2 divided by the probability of x2, okay? And we treat x2 as a constant, right? Because we will set x2 equal to x2 at time t. And so this will be the probability of x2, and the denominator is the probability of x1 and x2 if we integrate it across all values of x1. Okay? And so this just becomes a constant. Okay, so we can safely say that x1 given x2 is proportional to the joint distribution. Okay, so the probability of x2 is just a constant. So the conditional distribution is proportional to the joint distribution. Okay. All right, and in this thing, the joint distribution is equal to 1 over, we have all this whole thing. Can I, do I select stuff? Can I do this? So the joint distribution is equal to this. Okay. No. All right, and this itself, this is a constant as well. Okay, so we'll just continue on, and we'll say x1 given x2 is going to be just proportional to just the exponential stuff, right? And I'm going to kind of you know, exponents of when you add them, they're factors, right? So this will be proportional to e to the 1 over 2 1 minus rho squared x1 squared minus 2 rho x1 x2 times e to the negative 1 over 2 1 minus rho squared times x2 squared, right? Okay, and this part, this is just a constant as well. Okay, and then, all right, so let me just kind of expand this out. We'll do negative of x1 squared minus 2 rho x1 x2 and then I'm going to complete the square here. Sorry, wait. I need rho squared x2 squared minus rho squared x2 squared. I think I'm Is that okay? So if we complete the square, right? Completing the square, and then again, this is just another constant. So we get probability of x1 given x2 is going to be proportional to e to the negative x1 minus rho x2 squared 2 times 1 minus rho. Oh, I messed this up, sorry. put the parentheses on the wrong side. Sorry. Messy. Okay. And so looking at this is proportional to the normal PDF, where mu is equal to rho x2 and sigma is equal to 1 minus rho squared, right? Because if you recall, the normal PDF is 1 over 2 pi sigma squared, root 2 pi sigma squared, e to the negative x minus mu squared over 2 sigma squared. Okay, and so here we just say it's proportional to this, but really the only terms that we have are, mu is rho x2, and then 2 sigma squared is sigma squared is 1 minus rho squared, right? So there we have it. Okay, and then this part is really just the proportionality constant. Okay, so we have probability of x1 given x2 is equal to the normal distribution, where mu is equal to rho x2 and sigma squared is equal to 1 minus rho squared. And then by symmetry, we'll have, or basically using the same reasoning, we'll have that. Okay, and then all right, so the systematic Gibbs Sampler target PDF equal to normal this is what it'll be. We'll say let x at time t be x1 at time t and x2 at time t. And then we'll generate x at time t plus 1 as follows. X1 at time t plus 1 will come from the normal distribution with rho of x2 at time t, and sigma squared equal to 1 minus rho squared. And then x2 at time t plus 1 will come from the normal distribution, where mu is equal to rho x1 at time t plus 1, and sigma squared is equal to 1 minus rho squared. Okay, and then you'll have pretty much done all the work and boiled it down to this, and you'll have some exercises on the homework where you generate samples from the multivariate normal distribution, one using the Metropolis algorithm with a multivariate proposal, and then the other using the Gibbs Sampler using univariate proposals, or not even proposals, just univariate sampling for one variable at a time. Does that kind of make sense? All right, so maybe in the picture, and make sure you do your reading in the textbook as well. The picture is kind of like how do I draw? Is there a picture of I don't know if this is the picture I want. I mean, that looks nice. All right, we'll go ahead and copy this picture. How do I copy image? Okay. Can I do this? Paste it here. No. How do you copy pictures? All right. Right click. Download original file. I don't want that. Open image in new tab. Okay, sure. Copy image. Come over here, paste the image. Okay, I guess. There we go. Oops. Shoot. Okay, so we have this. And so the idea is, maybe I'll draw in red. You're starting off at some location here, okay? I don't know if you guys can see that. And so here we have x, I'm going to call this x1, and we'll call this, instead of y, we'll call it x2, okay? All right, and so the idea is, let's hold x2 constant. Okay, so if we hold x2 constant, then our how do I draw this? Then I have a curve that looks like this. Okay, so I've got some kind of normal distribution curve, right? This is our start location. All right, and so basically, at that location, my normal distribution looks something like this. Okay. At holding x2 constant, and then I just draw a random value, right? Draw a random x1. Okay, so let's say, from here, let's say I randomly select this location. Okay, so this will be x1 at time 1. Okay, so this will be our start location, x1 at 0 and x2 at 0. Okay, so this will be my new location. So when I draw this, all right, do I have a better colored tool? I color, let's do bright yellow this time. Okay, so maybe when I randomly draw, I select right here. Okay, and let me copy this image again. Okay, so the next iteration, now that I'm right there, oh shoot. Oh no, how do I do this? This is hard. shoot. Okay, let's try this. I want to put it right there. Okay, there we go. And then I need to, let's make this bigger. All right, so now, I don't know, it looks like I'm at like, I don't know, right here, okay? Where is that? All right, I'm gonna try to pretend like I can draw the same location here, okay? In yellow. All right, and we're gonna go, am I like right there? Does that look about similar? Not really. Something like right here, okay? So if I'm centered there now, if this is my, the random location I drew, then I condition based on this thing, and now my, my normal PDF traces this line and goes like that, right? So we're conditioning on that value, okay? And so it's like gonna be impossible. So now I have this thing, and then we just draw a random value from here, okay? So maybe value from this PDF, okay? And then you go back and forth, okay? So you select one value, and then you condition the distribution on that one value. You draw a random thing, and then you get a new value, you condition on that, and you draw a new thing, and you go back and forth, okay? And if you do that one at a time, then eventually, in the long run, you will have drawn values according to the target PDF. All right, is that okay? Okay. So if we're okay with that, with Gibbs sampling, I then want to introduce, because where Gibbs sampling becomes really powerful, all right? Because it feels like, you know, just for this simple multivariate normal case, the derivation of the conditional distributions felt like this is kind of hard, right? If I'd thrown it to you on a test and I never showed you anything beforehand, it would probably feel quite difficult to derive the conditional distributions, okay? But in Bayesian statistics, we are often set up in situations where the conditional distributions are kind of naturally flow out from the setup of your model, okay? So let me talk about hierarchical models, okay? So okay, so hierarchical models, this is kind of a natural pairing for Gibbs Sampler. Okay, in this, the conditional distributions the conditional distributions kind of are naturally flow out of the model. Okay, so do you remember when we first talked about Bayesian statistics, I used a model for baseball, and we said the probability, the batting average can be modeled with a beta distribution. Okay, so we'll go back to the baseball example for Bayesian statistics. Okay, and we said batting average can be modeled with a beta distribution. Okay, and so the idea was, your beta distribution varies from 0 to 1. Okay, 0.5, 0.3, and we said the distribution probably looks something like this, right? And then, and then we said, the probability of theta given the data is equal to probability of the data given theta times the probability of theta over the probability of the data, okay? And this thing, P of theta, is the prior distribution. Right. And I said, for the prior distribution, let's use a beta distribution with alpha equal to 81 and beta equal to 219, right? So I said, let's set probability of theta equal to the beta distribution with alpha equal to 81 and beta equal to 219, right? And many of you asked, how did you pick those numbers, right? And I didn't give a good answer. I said, these just seemed like good numbers that reflected my knowledge of baseball, right? And I was probably that, and some of you are like, okay, but it didn't feel like a great answer, right? Where did 81 and 219 come from, right? And I said, oh, these are good numbers to use that reflect, my knowledge. Okay. All right, so me, you. All right, okay. And all right, so now I will give you a better answer, all right? And well, it's not really a better answer. It's not going to answer where did 81 and 219 come from, but a solution to this is rather than just picking numbers like 81 and 219 out of the sky and saying, this is what I feel like, we can say, you know what, these numbers, 81 and 219, they themselves are unknown parameters to us that also need to be estimated, okay? Okay, so in a hierarchical model, we will also let the parameters of the prior distribution be random variables that need to be estimated. Okay. All right. So keep in mind, so for the baseball example, the data we observe are basically at-bats and hits. Okay, so we see, did the person get a hit? Did they make it to base or not, right? So what we observe are at-bats and hits. Basically, the outcome of each at-bat is going to be comes from what kind of distribution? So they go to the batter goes up to bat, and either the batter gets a hit or he doesn't, right? So that kind of outcome can be modeled with what kind of distribution? It's just a yes or no, right? So that's a Bernoulli, right? And what's the parameter in the Bernoulli? So the outcome from each at-bat comes from a Bernoulli distribution with parameter, I guess we'll say theta, where theta is equal to the batter's basically probability of getting a hit. Which is basically the batting average, right? All right, so that's the data that we observed. The at-bats and the hits, and the outcome of each at-bat is a Bernoulli distribution with parameter theta, okay? And then now we're going to say the parameter theta comes from the posterior distribution, okay? Well, parameter theta comes from some other distribution, right? Posterior distribution, which is the probability of the theta given the data, okay? Or not comes from, can be modeled. Which is equal to the probability of the likelihood times the prior divided by the marginal probability, okay? And then so the prior distribution of theta comes from is a beta distribution with parameters alpha and beta, okay? And now we say the parameters alpha and beta themselves come from another random distribution. Okay, so you can kind of see why we're calling these hierarchical models, because we have your data depends on some parameter, and that parameter depends on another distribution with parameters, and those parameters depend on some other distribution, right? And we could keep going and say, all right, alpha and beta are coming from some other random distribution which also has parameters, and those parameters come from another distribution, and we can keep climbing the ladder, right? Instead of going on to infinity with a whole bunch of random distributions that produce more parameters and finally get to the parameter that you want, we'll just say the distribution that produce alpha and beta will be what's considered an uninformative distribution, okay? An uninformative distribution is basically kind of like any value is possible, right? In the case of alpha and beta, we probably want to limit it to just positive numbers, and we might say the uninformative alpha will go from 0 to infinity or something like that. Basically, you just turn your prior distribution, the distribution from which alpha and beta come from will just be kind of flat, will be a constant, basically, okay? If it has infinite support, then a constant will technically integrate to infinity, and so, if you try to do the math, it could break, but if we're not going to bother with that, it's fine, okay? So kind of our picture from some other random distribution, and then we will basically we will use an uninformative distribution that has no parameters. To avoid having an infinite hierarchy. Okay, so it'll kind of look like this. We have uninformative, basically flat distribution. And from the uninformative distribution, we draw the value alpha and we draw the value beta. Okay? These two come together to form a beta distribution. And from the beta distribution, we draw the value theta. Okay, this will be the prior distribution. Theta, okay. And then the theta gets used for the Bernoulli distribution. And then the Bernoulli distribution produces 0, 1, 0, 1, dot, 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 which will be our data for at-bats. Okay, and so this is kind of the hierarchy. All right, plate representation basically won't represent the distributions in between. So this can also this whole thing can just go like this. Alpha and beta. I'm sorry, I should. Here, wait. Let me draw like another thing. So this will be theta for for we'll say player A, and this will be theta for player B. Okay, and player A will have his own Bernoulli that produce 0, 0, 1, 0, 1, something like that, right? So this is kind of the idea, is that different people have their own secret theta and something like this. Okay, so plate representation kind of simplifies this. Okay, so P for each player. So each player will have his own theta P, and then the Y sub i's will be for each at bat. Okay, so you might, if you delve further into hierarchical models, you'll often see plate representation. Okay, the idea of alpha and beta, this just basically means, and these arrows basically mean these define some parameter, and there's some kind of distribution that defines this, and it kind of just shows the hierarchy on which what values depend on which parameters. Okay, and the kind of the full diagram shows the different distributions and stuff, but I think plate representation is probably a little bit more common. Oh, we are out of time. Okay. Basically, when you have the hierarchical representation, the conditional distributions make sense, right? Y's are conditioned based on the theta. The theta is conditioned based on the alpha and the beta, okay? And then what about the alpha and beta? They're not really conditioned on anything. And so in this situation, you have to draw the random values. You want to estimate your theta and your alpha and your beta, and you've got a whole bunch of thetas to estimate, one for every player. And you condition them accordingly, okay? I guess we'll stop here for now, and I'll try to figure out what to put on your final exam based on this. I want to talk a little bit more about this on Tuesday a little bit, and maybe I can do also a little example, but don't worry about the stuff on Tuesday will not be covered. I won't put that on the final exam, okay? All right, with that, have a great weekend, and we'll see you guys Tuesday then.